The thermometer outside Earl Kowalski's workshop read minus 41 degrees Fahrenheit at 6:17 in the morning. On the 14th of January, not minus 40, not approximately minus 40, minus 41, the kind of specific, unforgiving number that separates theory from reality in the Alaskan interior, and the kind of number that had, 3 winters prior, split the south-facing log wall of his neighbor's cabin clean down the middle like a fault line opening up. The crack appeared overnight, running from the floor plate to the top plate, a full 8 feet of structural failure caused by nothing more dramatic than differential thermal contraction between a dry-fit log and its chinking. No wind event, no seismic activity, just cold, doing what cold does when a building hasn't been engineered to accommodate it. Earl was 67 years old that morning. He'd spent 31 years as a mechanical engineer for a pipeline construction firm operating out of Fairbanks, which means he has spent 3 decades solving problems that begin with the phrase we didn't account for. Permafrost heave under compressor stations, insulation failures on exposed pipe sections, anchor bolt pullout from frost-jack concrete pads. His career was, in the most precise sense, a catalog of what happens when standard engineering assumptions meet Alaskan ground truth. He retired in 2019, bought 40 acres near Delta Junction, and immediately began planning a structure he described in his project notebook, which he permitted me to read in full, as a shelter that doesn't fight the cold but ignores it. He didn't mean that poetically. Earl Kowalski is not a poetic man. He meant it in the strict thermodynamic sense, a building envelope so well separated from its thermal environment that the conditions outside become, for practical purposes, irrelevant to the conditions inside. The structure he chose to achieve this was a round Quonset profile, a continuous arch form with no vertical walls, no horizontal eve intersections, and no corner geometry. The reasons for this choice were mechanical, not aesthetic, and he walked me through each of them with the patience of a man who had explained load paths to project managers for 3 decades and had therefore developed an exceptional tolerance for starting from first principles. The arch, he explained, distributes compressive load along its entire curve rather than concentrating it at discrete points. In a rectangular structure, the load path travels vertically down the wall studs and concentrates at the corners in the foundation interface, which is precisely where frost-jacking, differential settlement, and thermal bridging do their worst work. In a continuous arch, there are no corners. The load distributes. The geometry is self-reinforcing. A round Quonset profile under a uniform snow load behaves more like a compression ring than a conventional framed wall, and compression rings, as any civil engineer will confirm, are among the most efficient structural geometries known. But before any of that geometry could matter, Earl had to solve the problem that defeats more cold climate builders than any other: the foundation. Conventional concrete slabs in subarctic conditions are a particular kind of slow disaster. The mechanism is well understood. Concrete has a thermal conductivity of approximately 1.7 watts per meter Kelvin. The frozen ground beneath it, depending on moisture content and soil composition, has a thermal conductivity ranging from 1.0 to 2.5 watts per meter Kelvin. This means that a concrete slab poured directly on grade in permafrost or seasonally frozen ground creates a direct thermal bridge between the heated interior and the frozen earth below. The heat flows down through the slab, warms the soil, and triggers what engineers call differential frost heave, the uneven vertical displacement of the foundation as ice lenses form, expand, and migrate through the soil column. The result, over 1 to 3 winters, is a foundation that no longer occupies the same plane it did when it was poured. Floors crack, door frames rack, walls tilt. The building slowly dismantles itself from the bottom up. Earl's solution was what he called a floating thermal slab, and the distinction between his approach and standard construction practice is worth examining in precise detail, because the difference is not large in material terms, but is enormous in performance terms. The standard approach involves pouring a concrete slab directly on a gravel subbase, sometimes with a layer of rigid foam beneath it. Earl's approach began with something fundamentally different. He refused to allow the slab to be in direct thermal contact with the ground at any point. He achieved this through a system of 4 distinct layers, each serving a specific and irreplaceable function, and he was emphatic that removing or substituting any one of them would compromise the integrity of the whole. The first layer was a compacted gravel pad, 12 inches deep, extending 18 inches beyond the planned footprint of the structure on all sides. This is not unusual. Gravel provides drainage and distributes point loads. What was unusual was Earl's insistence on the specific gradation of the gravel, a clean, washed material with minimal fines, specifically to prevent capillary wicking of groundwater upward into the insulation layers above. He tested 3 gravel sources before settling on one, running a simple capillary rise test in glass tubes in his workshop. A lot of builders use whatever's cheapest, he told me. I want a material that was hydraulically inert. The gravel bed cost him $1,100 more than the cheapest available option. He considered this a trivial expense relative to what it protected. The second layer was a continuous sheet of 6 mil polyethylene vapor barrier, lapped at all seams by a minimum of 12 inches, and sealed with compatible tape. This is the moisture control layer. Its purpose is to prevent ground vapor from migrating upward into the insulation above it, because insulation that absorbs moisture loses its thermal resistance in direct proportion to its moisture content. A dry mineral wool bat at R 3.8 per inch becomes something closer to R 1.5 per inch when saturated. Earl was precise about this. Wet insulation is a structural liability and a thermal liability at the same time. The vapor barrier costs $40. The failure it prevents costs everything. The third layer was what made Earl's approach genuinely distinctive. He installed 8 inches of expanded polystyrene rigid foam board, not extruded polystyrene and not polyethylene, both of which he considered and rejected for specific reasons. Expanded polystyrene, or EPS, has an R value of approximately 3.8 per inch at standard temperature, giving his 8-inch installation a center of panel R value of roughly R 30.4. More importantly, EPS retains essentially all of its thermal resistance when subjected to compressive loads typical of a residential slab, something that polyisosanurate does not do reliably, as its performance degrades under sustained compression. He installed the foam in 2 4-inch layers, staggering the seams so that no thermal bridge existed between the gravel below and the concrete above. The seams of the lower layer were covered by the solid field of the upper layer. Heat cannot travel through a gap that doesn't exist. The 4th layer was the concrete slab itself, 4 inches of 3,000 psi concrete with a 6x6 wire mesh reinforcement centered in the pour. Not 5 inches, not 6. 4, because additional concrete adds thermal mass inside the insulated envelope, which is desirable, but also adds dead load on the foam beneath it. Earl calculated the compressive stress on the EPS at the design load, including the weight of the concrete, the structure, furnishings, and 2 occupants, and determined that 4 inches of concrete produced a long-term compressive stress on the foam well within its rated capacity. He showed me the calculation, written in pencil in his project notebook, is the slab area for his 10-foot by 18-foot footprint, with a total estimated load of 20,000 pounds, including the concrete self-weight. The bearing stress on the foam came to approximately 12.2 psi, well below the 25 psi long-term compressive resistance of the EPS he specified. What this foundation accomplishes, in thermal terms, is a complete isolation of the interior floor surface from the ground temperature below. When the exterior temperature is minus 41 degrees Fahrenheit, the ground surface 2 feet below grade in Earl's location is approximately minus 8 degrees Fahrenheit due to the thermal lag of the soil. Without subslab insulation, that temperature signal propagates upward to the concrete and manifests as a floor surface temperature that can drop to mid-40s Fahrenheit, even in a heated structure, cold enough to cause condensation, cold enough to make the space uncomfortable, cold enough to drive substantial heating loads. With our 30 sublab insulation, the floor surface temperature in Earl's structure on the day I visited, when the exterior was minus 38 degrees Fahrenheit, was 61 degrees Fahrenheit. That is a delta T of 99 degrees across an 8-inch foam layer. It is also the difference between a floor you can walk on in socks and a floor that drives you toward the center of the room. The perimeter of the slab required additional attention because the edge of a concrete slab is a notorious thermal bridge. The insulation beneath the field of the slab does nothing to prevent heat loss through the exposed edge, which is in direct contact with the outside air. Earl addressed this with a continuous band of 4-inch EPS wrapped around the entire slab perimeter, extending from the bottom of the subslab foam to 12 inches above grade. This perimeter insulation was protected on the outside by a pressure-treated plywood skirt, which also served as the attachment point for the Quonset's base channel. The detail sounds minor. In practice, it eliminates what would otherwise be a strip of the floor perimeter that runs perpetually cold, produces condensation, and serves as a frost nucleation point at the slab edge. The total thermal resistance of the floor assembly, sublab, EPS plus the concrete's own modest thermal resistance, gives a combined assembly R value of approximately R32. For comparison, the International Residential Code's minimum requirement for slab insulation in the coldest climate zone is R10. Earl built to more than 3 times code minimum. Not because he was required to, but because he had spent enough time in buildings that met minimum requirements to know exactly what minimum feels like in January. I asked him whether the cost of the additional insulation, the difference between R10 and R32 in subslab foam, was justified by the energy savings. He looked at me with an expression I had seen before on engineers who have been asked to justify their work in purely economic terms. And he said something I want to quote exactly because it captures a philosophy I encounter repeatedly among serious cold climate builders. The insulation isn't there to save me money. The insulation is there so the building works. If it works, the money question solves itself. He then provided a number that answers the question more directly than any philosophical position. His structure, measuring approximately 160 square feet of conditioned floor area, maintained an interior temperature of 68 degrees Fahrenheit through the entirety of the previous January, the coldest month on record as location in the past 11 years, using a single small wood-burning stove consuming an average of 0.8 phase cords of split birch per month. A comparable rectangular stick-frame structure of the same floor area, built to standard code minimums, will be expected to consume between 1.8 and 2.4 phase cords per month under the same conditions. His fuel consumption was between 55 and 67% lower than the code minimum baseline. Over a 5-month heating season, that difference represents between 5 and 8 phase cords of wood, a material, measurable reduction in the labor of winter survival. The foundation took Earl 11 days to complete, working alone except for 2 days when his son drove up from Anchorage to help with the concrete pour. He rented a small concrete mixer and batched the material himself, working in 2-hour windows when the air temperature rose above -10 degrees Fahrenheit, which it did on 4 of the 11 days. On the other 7 days, he prepared forms, cut insulation, and ran vapor barrier. He kept a temperature log, entering readings at 7 in the morning and 4 in the afternoon. The log is meticulous. It reads like the record of a man who has learned that the difference between success and failure in cold environments is almost always found in the details that seemed optional at the time. The floor, once cured and dried, which took longer than it would have in a temperate climate, owing to the suppressed evaporation rate at low temperatures, became the first truly finished element of the structure. Earl walked across it before installing a single arch rib. He described the experience in his notebook with characteristic economy. Floor is warm. Bill can proceed. There is something worth pausing on in that sentence. A warm floor, in the context of a structure that does not yet have walls or a roof, is not an aesthetic luxury. It is a statement about the integrity of the thermal boundary at its most vulnerable interface. The ground is the largest thermal mass in the vicinity of any structure. It is always present, always in contact, and always conducting. Every decision Earl made in the design and construction of that foundation, the gravel gradation, the vapor barrier laps, the staggered foam joints, the perimeter insulation detail, was aimed at a single outcome, making the ground irrelevant. The arch structure that would eventually rise from that foundation presented its own set of engineering considerations, but the foundation had established a condition that makes everything above it possible. A well-insulated wall assembly cannot compensate for an uninsulated floor. Heat moves in all directions simultaneously, and any unguarded interface becomes a dominant loss pathway. Earl understood this from his pipeline work, where he had watched expensive insulation systems fail because a single thermal bridge, a support bracket, an uninsulated valve body, a gap in the cladding, conducted more heat than the surrounding insulation could offset. The lesson had been learned at scale, at cost, in the field. He applied it here, at the most fundamental level of the building, before any of the more visible work began. The drone that appears in photographs of Earl's completed structure was not his. It belonged to a neighbor's son, a young man of about 20 who had arrived uninvited one afternoon with a device and a request to film the build. Earl permitted it, with conditions. No talking, no questions while he was working, and no footage of the foundation detail, which he considered proprietary in a loose sense, not patented, but earned and not to be distributed without context. The footage the young man captured shows a completed shell from above, the corrugated steel skin gleaming in low winter light, the stovepipe exhaust rising vertically in still air, the structure sitting low and compact on its gravel pad like something that belongs to the landscape rather than something imposed on it. What the aerial footage does not show, what aerial footage never shows, is the 8 inches of foam beneath the concrete, beneath the floor, beneath the man standing inside in his socks at 68 degrees while the thermometer outside reads minus 38. That is the invisible work. That is the part that cannot be photographed or made compelling in a short video. That is the part that determines whether a cold climate structure is a building or an argument with winter that you are slowly losing. Earl Kowalski is not losing. He is, by every measurable indicator available to us, winning. Not through innovation in the dramatic sense, not through novel materials or experimental technology, but through the systematic application of principles that have been understood for decades and routinely ignored in the interest of building faster, cheaper, and less carefully than the environment requires. He told me, on the afternoon of my second day at his property, that the thing that surprised him most about building in the Alaskan interior was not the cold itself, but the way the cold amplifies every decision. A vapor barrier lap that would be meaningless in Georgia becomes a moisture intrusion pathway in January at Delta Junction. A foam joint that would be thermally insignificant in a mild climate becomes a frost nucleation line in a structure subject to delta T values exceeding 100 degrees. The cold does not introduce new physics. It makes existing physics consequential in ways that moderate climates permit you to ignore. He has been asked by several people who learned the project whether he would build the same way again, knowing what it costs in time and labor and careful thought. He said yes, without hesitation, and added one qualification. He would start with the foundation documentation before beginning to pour, because he had made the mistake of trusting his memory for several of the foam joint dimensions and had to reconstruct them from measurements after the fact. The notebook, he said, should precede the shovel, not follow it. This is the advice of a man who has watched projects fail not from lack of knowledge, but from insufficient respect for the gap between knowing something and having it written down where you can refer to it under pressure in the cold when your hands are numb and the concrete truck is waiting. The field report for today ends where the foundation ends, at the base channel, where the first arch rib will be bolted in tomorrow's session, weather permitting. The forecast calls for minus 29 degrees Fahrenheit, with light winds from the northwest. Earl considers this workable. He has insulated gloves, a thermos of coffee, and a project notebook with the next 4 steps written out in advance. He will proceed methodically, as he always has, because methodical is what the environment requires, and what 31 years of pipeline engineering produce in him as a reflex rather than a discipline. The slab is warm. The build will proceed.